So the next step in the problem is to get some intuition as to how we go from the uncoupled basis to the coupled basis. The uncoupled basis were just simple tensor products. The coupled bases are linear combinations of those tensor products, so they're entangled states, and they will be eigenstates of the total angular momentum. So let us see what we have in our hands. We're summing orbital angular momentum and spin angular momentum to form total angular momentum. You can think generic as L as the first angular momentum that you're adding and S the second one. Then notice that the Jz is Lz plus Sz, and typically these are, their eigenvalues are proportional to h bar, so many times we like to divide them by h bar to get pure numbers. There's a very useful formula that we need here in our calculations, and it's the action of the lowering and raising operators. So in general, for any angular momentum, not just for the sum, the raising and lowering operators change the value of m and give you this thing times the raised or lower state. So these are formulas that are valid for L, in which case you have L and M, or for S, in which you have S and MS, so for anything, and we'll use it a lot. Now, what were the states that we're talking about? They were states of L and M and S and MS, was actually L equals 1 and S equals 1/2. And those are like J1 and M1 if you're adding two arbitrary angular momentum, J2 and M2. Now we had 6 states. Remember, there's 3 of these, 2 of this, and I've organized those states here. I want you to look at those states because they really, this organization, this table, in fact, solves half of our problem. Once you realize how this table is built, you've understood something very important. I've organized it in the following way. I picked a state with the highest possible value of m and the highest possible value of ms here. So this is always, the first entry here is always 1. This can be 1, 0, or minus 1. This entry always 1/2, and this could be plus 1/2 or minus 1/2. And therefore, this state has the top values of m and ms, and you could ask, what is the value of jz? But jz is lz plus sz. So if you try to figure out what is the eigenvalue of jz of these states, you have, in fact, that this has a definite value of jz. It's lz plus sz, so it's 1 plus 1/2. If that confuses you, you should think of this lz plus sz operator coming here. The lz acts on the first state, so it goes here. And that term gives you the eigenvalue here, which is 1 times h bar, and does nothing here. The sz comes in here and says, oh, I belong to the second state, and gives you 1/2 times the whole state. So you get 1 times the whole state from lz, 1/2 times the whole state from sz. Therefore, the naive thought is true. The value of jz of this product state is the sum of lz plus sz. So it's 3/2. Now that we say, oh, wow, surprise, you could diagonalize jz without forming linear combinations, and that's true. So what other values of jz can you get? Well, this can be 1, 0, and minus 1, and this minus 1/2. So you're going to go down by values of 1. So you can go 3, 1/2. How do you get 1/2? You cannot get 1. There's no way to have an integer and a half integer add to give you an integer. So you next go 1/2, and here you can obtain it in 2 ways, with a 0 and a 1/2 here, or a 1 and a minus 1/2 here. There's no other way. So there are 2 states here. This is very important. There's 2 states with jz equal 1/2. With Jz equal minus 1/2, there are two states as well, with a 0 here and a minus and a plus. And finally, at the bottom, with the lowest possible value of m and lowest possible value of ms, you have one state. This is a state with Jz equal minus 3/2. So these are our states organized nicely by the eigenvalue of Jz. But although they're eigenstates of Jz, these are not quite eigenstates of J squared. And we are still not done because we need eigenstates of J squared. Eigenstates of the total angular momentum should be eigenstates of Jz and J squared. So, but we can actually tell what we have. So here we are supposed to form states that are eigenstates of J squared and Jz. So we're looking for eigenstates of states Jm, where this is the eigenvalue, well, of J squared, more precisely is h squared times j plus 1. And this is the eigenvalue of Jz over h bar, or h bar m. We're trying to find eigenvalues of this type, eigenstates of this type. And now, you know, in angular momentum, we do have a state, we have states with Jz equal to 3/2. But we don't have states with Jz equal 5/2 or higher. So the maximum value of Jz is 3/2 in this list. So what kind of J could you have that has a Jz of 3/2? Well, if J would be equal to 1/2, m cannot go that high. M is restricted to the value plus j and minus j on all the integers in between. So if you had j equal to 3/2, you would have, yeah, Jz could be equal to 3/2. If you had j equals to 5/2, Jz could have also 3/2. But if you had j equal to 5/2, you should also have a state with Jz equal 5/2, because you have to have the full multiplet. You see, by the time these states arrange themselves, they have to arrange themselves into full multiplets. That is the key idea. It's the key statement of representation theory of angular momentum. These are states that form are representations of L and of S. If you act with L of these states, you scramble them. But you remain between this space of states. If you act with S, you scramble them. By the theorem that we've proven about angular momentum, then the sum of the two must also form representations. So you must have full representations. If you had a J equal 5/2, you would be missing the state with Jc equal 5/2. So the conclusion here is that we must have a multiplet with J equal 3/2. Equal 3/2 must be present. And this corresponds to 4 states. M equal 3/2, 1/2, minus 1/2, and 0. Now, the state J equal 3/2 and M equals 3/2, the only state that can be is the top state, because it's the state that has M equals 3/2, Jz equals 3/2 h bar. So this state must be the state 1, 1, 1/2, 1/2. Now, how about the state J equals 3/2, M equals 1/2? Well, that's a little more dicey because there are 2 states with M equals 1/2, this and that. Which one is it? Well, most likely it's a linear combination. Otherwise, it just would be too trivial. And I don't know yet how to do that. So we'll do this. J equal to 3/2, M equals to -1/2. I don't know how to do it either. But J equals to 3/2 and M equals to -3/2. There's only one state with M equals -3/2. So this state must be the 1 minus 1 tensor 1/2 minus 1/2. So we've identified two of the states of this multiplet that must be present. So two states have been identified. That's great progress. And in some sense, if you just wish to calculate the energy splittings of the LS coupling with what I'm going to say now, that would be all you need. But we want to look a little and to get some intuition about how this entanglement of L and S works in order to form the states with of the total angular momentum. So we have four states here with J equal 3/2 present. But there were 6 states, and we are not going to change the dimension of the vector space. We're just trying to find another basis. So 6 vectors to begin, we must have 6 states. So we must have 2 more states. So what multiplet would have 2 states is a J equals 1/2 multiplet. Must be present. And you can say, well, how about 2J equals 0 multiplets? That's not possible, because actually what's going to happen is that we have 4 states that have either, in total, m eigenvalues that are either 1/2 or -1/2. So there's no states with 0 value of m, so J equals 0 is not present. J equal 1/2 is therefore present, and there's just 2 states. So actually, what we are saying mathematically is written in the following way. We say that L equals 1, which is 1, tensor S equals 1/2. So the 1 here doesn't mean the number 1, means L equals 1, tensor with S equal 1/2, what we've been doing. 1, L equals 1, tensor 1/2. It actually gives us a J equal 3/2 direct sum with a J equal 1/2. So this is, in a way, encapsulates the whole physics of this. So this means L equals 1 times S equals 1/2 gives you J equals 3/2 plus J equals 1/2. And in terms of number of states, it's the fact that 3 states here multiplied, because the dimensionality of this is the dimensionality of the first times the dimensionality of the second. These are 3 states, 2 states. Total dimensionality was 6, as we know. And here the dimensionalities add in the direct sum of vector spaces. This is dimension 4 plus 2, dimension 2. So this funny looking equation is really the same as saying 3 times 2 is 4 plus 2. It's a very nice thing. So actually, those are the eigenvalues of J that you get in the tensor product. So these are the coupled states. And since L dot S could be written in terms of J squared, the values of J squared are determined, and you can find already the energy splits. But we'll leave it for a few more minutes and try to complete the construction of this coupled state. So Our problem is here that we don't know what these two states are, and we don't know what are the j equal 1/2 states, 2 more states. So it all arises because in the list of states that we have here, we have 2 here and 2 here. And some linear combination belongs to the j equal 3/2 multiplet. Some linear combination belongs to the j equal 1/2 multiplet, and the same for these 2 states.